Hey, it's Jim, and this is FRM Part 1, topic on quantitative analysis, and the chapter on hypothesis testing, which is a natural progression from our previous chapter on the sample moments. Let me just quickly remind you that, remember, we had a population which includes all of the data in a certain population. Maybe we're interested in the population mean and the population standard deviation. We call those parameters. But it's not very often that we have the entire population. And even if we have the entire population, we're not quite sure if we want to go out and spend all the energy and the resources and the time and the money to collect all the data of the population. So what we do is we take pockets of that population and we call that a sample. And we can calculate the sample mean and the sample standard deviation. We call those statistics. And what we're thinking of is that we're thinking that those sample means and standard deviations and maybe some other statistics represent the entire population. So in this chapter, what we're going to do is we're going to test whether or not those samples that we collect, is it representative of the entire population. Think of it almost like two people arguing. You have one person who the population is represented by the population who's always right. You know, the population is whatever it is. And you take a sample and that sample is kind of arguing, is kind of challenging. It's not a fight or anything like that, but we're saying, you know what, let's take a sample and see if it looks like the population. And that's pretty much what hypothesis testing is. Now, based on my summary, if you look at these learning objectives, you might say to yourself, gosh, Jim, did you say anything in that introduction that looks like any of these learning objectives? And the answer is, well, of course I did, but I implied a lot of things. Let me just remind you, as I always do, you have 100 questions on the exam, so maybe there are 2 questions from this chapter. What are the most likely 2 questions in here? That's a tough one. There are great questions for almost every one of these learning objectives. You know, the first one is really important. Second and third are really important. You know, how to construct confidence intervals and using p-values. I mean, those right there, that pretty much is the bulk of this chapter. So it's probably likely that at least one of those questions will show up out of those first, 5 or 6. And then maybe we'll do the difference between 2 population means. We'll do that towards the end of the slide deck. That's relatively easy. And then this idea of multiple testing and how it can bias, I have just kind of a short editorial on that at the end of the slide deck. All right, so let's figure this out. So if 2 people are arguing, you have one person who says, you know what, Michael Jordan's the greatest golfer. Michael Jordan's the greatest basketball player ever. Someone says, no, LeBron James is the greatest basketball player. So you have this argument. Now, the question then becomes, in this argument, which one is the population, which one is the sample? And so my idea is not really that it's not completely perfect, but what you're doing is you're making a comparison about some idea or some characteristic of the population. How about a better example might be that, hey, here's the population of all NBA players in the history of the NBA. Here's a sample of one, Michael Jordan, and I'll say something like, you know what, Michael Jordan is no different than anybody else inside of the NBA. That would be our null hypothesis. But if we think Michael is the best player, then we would want to set up the alternative hypothesis that says, oh, the null is Michael is no different. The alternative is Michael is better. And then we try to find evidence that Michael Jordan is better than the average person or all of those people inside of the population. So this is what I'm saying. Look down at that third diamond point. We assume that the null hypothesis is true unless we provide lots and lots of evidence. And the lots of evidence is going to give us some idea about percentiles and probabilities. We're probably going to say something like, hey, with 95% confidence, we can say that Michael Jordan is no better than the average player in the NBA. But of course, we look at his stats, we're probably going to reject that. We'll probably accept the alternative hypothesis. We have a couple of slides here, and I'll show you that explicitly. But notice we have a judge. That dude looks a little bit like my father. That's a little bit scary for me right there. I think this is a super important slide. This is essentially what hypothesis testing is all about. We're going to state the hypothesis. Now, I have a simple and silly example with Michael Jordan, but maybe we want to say something like, hey, there's a particular stock out there that we think is undervalued, and therefore we're going to invest in that undervalued stock. So we would state the hypothesis that, hey, this stock is no different than anybody else, and then we would collect our evidence as good financial analysts to prove that it is, in fact, an undervalued stock. Now, of course, this is not based on opinion. This is based on an assumption of either normal distribution or nearly normal distribution. So we can use some test statistics that we've talked about in the past, like the Z statistic or the T statistic, and we have to figure out which one is which. And then we need to define our level of significance. Do we want 95% confidence? Do we want 98, 99, 99.9? In fact, when we get to, I think it's in book 3, when we get to our study of copulas, we'll look at a Vasicek model. And there's some really good examples inside of the chapter where we're going to do a 99.9% level of significance. I'll talk a little bit about that later on. And then we need to make a decision rule regarding the hypothesis. In other words, we're going to accept if this happens and reject if this happens. Then we'll calculate the sample statistic. Maybe we'll go out and collect that data on that individual stock and look at daily returns or weekly returns or monthly returns. Or we can look at Michael Jordan's points per game or steals per game or any of those kind of sample statistics, and then we'll make our final decision. So that's pretty much the process of how we conduct a hypothesis test. And of course, we need to go through each one of these individual steps, and that'll take us virtually the entire slide deck. So let's focus and be prepared for every one of these steps to show up on the exam, and then probably one or at least one, maybe two of them will show up on the exam, and you'll be ready for it. So here's the null hypothesis, always noted as H sub O. That statement is that there's no effect or no difference. What did I say? Michael's no difference than the rest of the NBA. This stock is no different than all the stocks that trade on the New York Stock Exchange. What we do is we assume that that null hypothesis is true. So we can say mean return is 0, or we can say there's no correlation between assets. And that's going to serve as the benchmark return. Now notice down at the bottom, we've got the little key idea here. What that does is it tells us that on the floor of the New York Stock Exchange and in the NBA, there's lots of noise out there, whatever that noise means. And what we want to do is not be overly or, in fact, any influenced by that noise. The alternative hypothesis, which oftentimes is H sub 1, is pretty much just the opposite of H sub 0. All we're doing is saying that, okay, this particular stock is undervalued. Michael Jordan is superior than the rest of the NBA. Notice that third bullet point. That's a good question. It's a departure from the status quo. Now, what's interesting about the alternative hypothesis and the null hypothesis is that they don't have to have the same sign. And let me go back here real quick. Here we have the examples are that the mean return is 0. So the alternative hypothesis could be that the mean return is not equal to 0. Or we could say the mean return is positive, or the mean return is negative. So this is an important concept, this idea of a one-sided or a two-sided test. And we're going to see this when we look at what's called a critical value in just a few minutes, because when we select the Z stat or the T stat, we're going to have to figure out, do we put do we put that 5%, if it's a 95% level of confidence, do we put 5% in one tail, or do we chop it in two and put 2.5% in each tail? You'll see an example as we go through there. Notice the bottom bullet point, it gives the direction of the test, like Michael Jordan is better. I mean, we could have an alternative hypothesis that says Michael Jordan stinks, right? That would be less than the population. Here's the example we came up with. This is a little bit more applicable than my Michael Jordan or maybe just some random stock out there. So we have a hedge fund. Here I am, Jim's hedge fund. I'm the manager, and I can say something like, you know what, I'm smarter than everybody else out there. I can generate positive alphas no matter what. In this case, we talk about, central bank liquidity. So maybe I'm an economist and I'm an expert on what the central bank is doing. I can read between the lines when Jerome Powell says something in one of his interviews, and I can say, oh, he just said that. Therefore, I'm going to go ahead and do this, and I can generate a positive alpha. So notice the null hypothesis is going to simply be that, you know what, I'm just a regular person. I'm a regular hedge fund manager, and I'm not going to be able to generate any kind of risk-adjusted expected excess returns. So notice that alpha is equal to 0, but the alternative is going to be not just that the alpha is not equal to 0, because then that alternative would be, well, I'm either really, really good or I stink. But I'm thinking that, hey, I'm really, really good, so that's why we have a positive, a greater than sign after the alpha, greater than 0. Now, here's the deal. On the exam, it's a logical question for GARP to give you that those two yellow bullet points up there and say, hey, form the null and the alternative hypothesis. And they could have 4 choices, and the null hypothesis could be equal to 0 or greater than 0 or less than 0 or something else, right? You have to have 4 choices on the exam. And then the alternatives. You have to reach in and read. You have to read the supposed thing in the question stem to know if you're going to use an equal sign or a greater than or less than sign. Now, why are we doing this? Because if I really am superior, then I would like to advertise that I'm superior, or at least report to my investors that I am superior. And so I can go ahead and say, you know what? I think I'm pretty good at this stuff. And this is what I've done over the last year or 3 years or 5 years. And here's the statistical proof that I have outperformed other hedge funds or outperformed the population of hedge funds. And so notice what we have in the gray. That's not gray. What is that? Light orange, whatever color that is. Well, we want to make certain that I'm just not lucky. Maybe I'm in the background just flipping a coin, saying, okay, let's pursue this macro hedging hedge fund strategy. Flipped a coin and we do that. And I was right. And then the next day I flip a coin and say, okay, we're going to go ahead and find a bankrupt firm or a near bankrupt firm. I'm going to invest in their bonds. Oh, it says invest. Okay, I'm right. So we want to make sure we distinguish between my skill set and luck. Once we have put together that null and alternative hypothesis, we need to move down that list of the steps in hypothesis testing, and we need to craft this test statistic. And so all we're going to do is we are going to take the difference between what we think something is. Notice in the red box, there's that hypothesized value, and the sample statistic. And that sample statistic could be the mean or the standard deviation. But here's the deal. This is why I was saying to you earlier that think of it as two people arguing. And it's not really an argument, but that's represented in the numerator. We have the hypothesized value and the sample statistic. And so we have a minus sign in there to see if there's a difference between the two people. I always think, I'm not a big baseball guy, but there's the umpire behind home plate, and he's crouching down, and he goes, "That's a strike." And the batter turns around and says, "Are you nuts? There's no way that was a strike." But here's the thing. The umpire is the population, because whatever the umpire calls, that's the correct call, right? And the batter is influenced by lots of other things, sunshine, the pitch, and the first baseman, all that kind of stuff. So there might be a bias in that sample. And so I think it's okay to think of it as an argument, but it's not really a battle or a fight. But that's why we have a minus sign in the numerator. And then what we have to do, like we do in many, many instances, is that we standardize this test statistic. And the way we standardize is we just divide by the standard error. So inside of that standard error is a measure of standard deviation, the degree of error, and that gets us our test statistic. And I'll show you here in just a second. We have some slides where we're going to draw a picture of a normal distribution, and I'll show you where that test statistic falls, whether it's a z or a t or even a chi-square. Now, this slide here is a little bit of a reflection of my argument between the batter and the umpire. When I was saying the pitcher and the sun and the first baseman, that's kind of the noise, right? And the noise is going to influence whether the batter thinks it's a strike or a ball. Of course, it's right down the middle. That's an obvious strike. But look over on the right side of our illustration. There we go. There's how clear that signal is. And notice it's going out that way. And so if we have a large test statistic, that's super strong evidence that we're going to reject the null hypothesis. If it's a weak signal, if there's tons of noise out there and the signal can't get through the noise, well then we're going to fail to reject the null hypothesis. Now look down at the bottom in the little light bulb. We're going to have a rejection region and we're going to have a non-rejection region, and you'll see that here in just a second. Let's get back to this idea of a one or two-sided test. If the question stem reads something like, "Oh, better than" or "worse than," that's probably just one direction, so you're going to use the greater than. A two-sided test is in which you're going to use an equal sign or an unequal sign. That unequal sign is for the alternative hypothesis. So that determines whether it's the left tail or the right tail, one tail, or both tails. So when the direction matters, that general form is going to be the alternative hypothesis is that there's the greater than or the less than sign. So there's a fun performance versus a benchmark. What happens then, if we have a one-tail test, then we're putting all of that confidence level in one tail. So remember I said if we have a two-tail test, we have to chop that, and let's just assume a 95% confidence, we have to chop that 5% into 2.5 on the left tail, 2.5 on the right tail. But if we have a one-tail test, this is known as a power boost. We throw all of that 5% in the right tail or all of that 5% in the left tail. Now, this is going to be super important. We have talked recently about value at risk and expected shortfall. Those are going to be one-tail tests because all we care about is that left tail of losses. Here's the first of a couple of slides that I promised you just a few moments ago. Notice that we're looking at a one-sided test. Look on the left graph. There's a right tail test where we have a greater than. Notice on the right side we have a less than, so that's a left tail test. So notice that we put all of our confidence level in the right tail, so that's red. In the right column we put everything in the left tail, so that's blue. Now we're assuming here that we've got an alpha of 5%. So we throw all of that 5%, and the z-score is 1.65. And it's positive 1.65 for the red, negative 1.65 for the blue. I'm not sure that that's a really great exam question to have the choice between those two, but you should be prepared for something like that. By the way, I'm going to give you some advice right now that it's probably going to be beneficial if you begin memorizing now some of these Z values at 95 and 98 and 99 and 99.9 and 99.5, so that you don't have to worry about looking on the tables when you're taking the exam. Now remember, you can't take tables in with you, so what GARP will do is they'll give you a question stem and they'll give you a partial Z table, and you'll have to try to figure it out. But if you have them memorized, you won't have to waste any time doing that kind of stuff. How about a two-sided test? This is when the sign is unknown, when we don't really care whether it's positive or negative, or whether excess returns are positive or negative. What we want to do is we want to say that it's significantly different from something, so that that alternative hypothesis in this case is going to take the form of a not equals. So there you go. See that second bullet point, that the population mean is not equal to the sample mean. What we do is we split the alpha into two parts. So back here, all of that alpha is in the one tail, right or left. So the z-score is 1645, or 165 if you want to remember it. But if we split it into 2.5, then the z-value is 1.96. And there you see this with the second illustration of the normal distribution. And so notice up at the top, what we need to do is chop the alpha, that confidence level of 5%, in half. So we throw 2.5% in each tail, and the critical value of C is 1.96. When I was in graduate school, my professor, my econometrics professor, he always said, you know what, of course it's 1.96, but when you're looking at output results, just think about 2.0. That's how I remembered that. Now this is one of those very interesting learning objectives, and I think this is a likely question on the exam. So we got the hypothesis, and then what happens if you make mistakes? And that's what a type 1 and a type 2 error are. They're just mistakes. I want you to think about this. A type 1 error is, I'll give you an example. It's investing or accepting and investing in an overvalued stock. A type 2 error is rejecting an undervalued stock. So a lot of statisticians will always say, look at the second diamond point there. It's a false positive. But for me, false positive, for me, and the way I think, using the example that I just gave you, investing in an overvalued stock, that brings it more to light inside of kind of the investment and risk management universe. But I think it's good for you to remember false positive. Now notice the fourth diamond point there, 1%, 5%, 10%. You could pick anything. You could pick 2.5%. You could pick 80%. You could pick almost any number. But historically, at least going back to like introductory statistics classes, it's almost always 5%. But we're going to learn, and maybe we did learn this back in expected shortfall, maybe we want 99% or 99.5% or 99.9%. Think about this. If we do value at risk, we want to be as confident as we can that whatever shows up in that little teeny weeny part of the tail doesn't happen over the next 10 days. And if it does, we need to be ready for it. So if the type 1 error is a false positive, then the type 2 error is a false negative. And, over here, you can see that type 1 error. That's easy to remember. That's all the way to the right, kind of like the one directional test. But here, we need to look at the combination of some colors here. So that type 2 error is what color is that? Is that purple or blue? Now, I've been hinting about this power of the test. Remember we did like a power boost just a few minutes ago. So remember that first definition up there is correctly rejecting a false null hypothesis. And that that beta, that Greek letter for B, the B is the probability of a type 2 error. So the power of a test is related to a type 2 error, and you can see the definitions right there. What that means is that a higher power means that the test is super sensitive. What are the determinants of power? This makes sense, right? Sample size, the impact size, and the test size. Here's a great slide for you to take a picture of. There's some examples with my dad as the judge in that one of those first slides about convicting an innocent person, etc. So take a picture of at least the top of this here, so you can so you have that memorized. Let's continue down on those steps of hypothesis testing and talk about the decision rule. And so this gets back to what I was saying earlier about, the near argument, or the battle between the batter and the umpire, or the difference between what goes on an individual stock and the floor of the New York Stock Exchange. So the test statistic and the critical value. So the test statistic we calculate, we did that a couple slides ago, and then the critical value we get from the tables. And I was telling you that you should probably memorize these things. And so this is really the end of the battle. If the test statistic is greater than the critical value, then we make some concluding remark. And if it's just the opposite, then we make the opposite concluding remark. And that's what's summarized down at the bottom. And so notice all we're doing is we're taking the test statistic, whether it's the absolute value or not, and seeing if it's greater than or less than the critical value with the alpha, which could be 5% or 1%, right? So if it falls outside the rejection region, then we fail to reject. If it falls inside of the rejection region, then we go ahead and reject. And we have a really cool example here in just a few slides. So pause on how this works, but remember that the difference between the test statistic and the critical value is the end of the battle, right? We're going to say, okay, you know what? It was a strike or it was a ball. Either way. But first, I want to spend a couple of slides on confidence intervals here. So what we're going to do is we're going to say something like, you know what? We have all this data, and we would like to know how far can we squeeze that data so that we can make a reasonable conclusion. And so this is pretty much what a confidence interval is. It's really just a minimum value and a maximum value given some level of confidence. So look down at the example. If we have a 95% confidence interval, there's our alpha, that's going to be 5%. We might come up with a confidence interval with a range of 15.5 and 16.2. What we say then is that with 95% confidence, the sample statistic, let's say it's just the mean, is going to fall within that range. 95% of that time, it will fall within that range. Now, if we want to do a 99% confidence interval, then the range might be, and I'm just making these numbers up, 14.8 and 17.6 or something, so the 99% confidence interval is going to be just a little bit wider, because now we're saying 99% of the time our test statistic is going to fall somewhere within that range. And it doesn't make any sense to do like a 30% confidence interval or a 42% confidence interval. So on the exam, be prepared to compute 95, maybe 99, and you're going to use this equation right here. So what we're going to do is take that point estimate, that's going to be the mean, and we're going to plus or minus, we're going to add and subtract some reliability factor here, and that depends on the confidence level. Right up top we have 95%, and then we're going to multiply that by the standard error. So standard error is a function of standard deviation, when there's lots of standard deviation, remember there's lots of risk, because then you're going to have a wider confidence interval. You're going to have to say, oh my God, here, let me go back here. If this thing had a really super high standard deviation, maybe we'd have to say, 11 all the way up to 21. That would be a wide confidence interval because of that degree of error, because of that standard deviation. Now, what did I say in that previous slide? I said that point estimate could be the mean. So there's the X bar, and there we're going to do plus or minus, and there's the Z score. And since it's plus or minus, it's a two-tailed test. So you have to divide the alpha by 2, and then we're going to divide by, there's the standard deviation in the numerator, and we divide by the square root of n, and we call that, back here, we just call that the standard error. So here we go. Look at those colors, and then these colors are the theoretical, formula for the confidence interval. Here's the practical formula for the confidence interval. Notice that we have a known variance, and we can throw that known variance in the numerator over in the orange box. There's a picture of our normal distribution. There's alpha divided by 2, so it's two-tailed. So we throw all that stuff in. We cut it in half and put half in each tail. And so that confidence interval is the space in between. So notice we've got 90, 95, 99 going down the left-hand column, and down the far right column, there's some check marks. So here's what I was saying to you earlier. Just memorize these things. 1.645, 1.96, 2.57. What was I saying earlier? You're going to have to do the 3.09 when you do that copula with the Vasicek model, 3.09. That's going to be a humongous formula that you're going to have to memorize for the exam. But my advice is just to memorize those, so you don't have to waste time on the exam looking at some partial table that GARP gives you. Now, back here, where am I? Back here, we knew the variance of the population, which we hardly ever do. Here, we don't know the variance of the population, so we calculate the sample standard deviation. So look here. So there's the lowercase Greek sigma. That indicates population. Here we have an S. That's the regular old English alphabet. That indicates sample. And then notice that instead of Z, let me go back here, instead of the Z, we need to use the T distribution there. Now, when we use the T distribution, we have to worry about degrees of freedom. We did all this in some of these previous chapters and slide decks where we divide by n-1, and that avoids any bias in there. Here's a good summary table. Go ahead and just take a picture of this. This just summarizes what we did over the last 5 or 10 minutes. So here's the example that I was warning you about. Let's suppose that we have 10 students. And here is the number of hours that these random sample of 10 students studied. Boy, that doesn't look like it's too wide. Gosh, I wonder how many hours I studied for that thing. How about if I tell you I studied for 600 hours? Well, that would be a lie. I wouldn't tell you that. I never kept track of my hours, but I don't know. Maybe it was 200, maybe it was 300. Who knows? Anyway, here's the question. Calculate a 95% confidence interval. So the first thing that we need to do is to compute the mean and the standard deviation. Now, I showed you this in a previous slide deck, but I'm going to go ahead and show you this again with the 12C. Now, I'm hoping you guys remember this, but I'm guessing that some of you do not. So let's just do this quickly. We have 10 observations. We're going to use our orange and blue functions, and we're going to use our sigma plus button down here. So all we're going to do is say 318 and hit our sigma plus. Notice it says that was the first one. So let's do 304. There's our second one. 317. There's our third one. 305. 309. 307. I know this is not very exciting. Maybe you're listening to some rock and roll music in the background while I'm babbling there. So what am I up to? 309. Did I do that right or did I? Well, we'll know. We'll know if I did it right. 327. All right, so we've got 10 of those things in there. So here's the mean down here, and there's the standard deviation. So we just do gold standard deviation. I'm sorry, gold mean, 312. Gold standard deviation. So there we go, 3.1 or 312, and then we rounded up to 7.2 there. So hopefully that was helpful. Boy, not quite sure what GARP would do. Would GARP give you, let me go back here. It seems a reasonable question, give you those 10 things, do the confidence interval, asked you to compute mean and standard deviation, but then again, it might give you this stuff and say, hey, here's the mean and here's the standard deviation. On the other hand, it may not even give you those 10 number of hours. It may just say, hey, here are 10 candidates and the mean is 312 and the standard deviation is 7.2. Construct a confidence interval. All right, so here's a couple of things that we needed to have memorized. I told you to take a picture of some of those. What did we do? We took a sample of 10. So we don't know what that population variance is. So we calculated it, which means we can't use the Z. We need to use the T. Also, we're going to use the T because the sample is less than 30. So there we are in blue. We've got 312 plus or minus. There's our critical value. Now, it's not on this page. So go back here. What do we say? 95%. So we need to chop that in half. So 2.5 and 2.5 on either side. Oh boy. So notice what we have boxed there. 2228 and 2262. So you should remember both of those numbers, and you'll know that degrees of freedom at 9. Don't do the 10 because you know that one of those possible answers is going to be the confidence interval at 2.228. Make sure you do the 2.226. There's the 7.2 that we calculated divided by the square root of 10, and you get 307 to 317. Now the next part here says something like, all right, that confidence interval that we just did, is that a different test than the hypothesis test that we did earlier? Or are they the same tests? And the answer is that it's two different ways to skin a cat. And essentially, both the hypothesis test and the confidence interval, they use the same stuff, but they arrive at the same decision in a different manner. So we have some colored boxes there to explain this. So both tools, statistical inference, right? Plausible range, a specific claim for the hypothesis test. So look down at the bottom left. They're mathematically equivalent. That's what I was saying. And they're going to have the same conclusion. So here's a picture over here on the right. So notice that we have a confidence interval. Is that purple? So we have the purple lines there. That's the confidence interval. Now, the horizontal axis, which is, what color is that? Kind of reddish brown, whatever that is. Imagine that there's a normal distribution above it somewhere. You know, maybe we're on the right tail, maybe we're on the left tail. It doesn't really matter. Maybe we're in the middle. So what we can do is we can compare the hypothesis testing versus the confidence interval. So look at the decision rules. We have a red and a blue there. If the mean, the hypothesis is u sub 0, if that lies inside the range. So there we go. There's the null hypothesis, HO, that's inside the range. So we fail to reject. We say it's normal. Michael Jordan is just a normal basketball player. But if it lies outside the range there in the orange, then we say, oh, Michael Jordan is superior. So there's an example down there for the confidence interval, 2.1 to 4.3. If that mu is 2.5, we're going to fail to reject it. But if it's 1.5, it's to the left, then we're going to go ahead and reject it. So we arrive at the same decision, but one uses the normal distribution and one uses the range. Now, a couple of extra things here that we need to know about hypothesis testing. If in fact the underlying variable is normally distributed and the variance is known, we're going to use the red box there. We did that in a previous slide. A couple of extra things here that we'll add to our conversation is that we're going to use the z because we know that variance. And our decision rule is going to be reject that null hypothesis if that z-stat falls within inside of that critical region. So in this slide, what we're doing is showing you that you use that z for both confidence intervals and hypothesis testing. If the variance is unknown, we've got to use the t distribution. And notice that in the denominator, there's the lowercase s. That's the sample standard deviation. But the cool thing here is that once you identify whether the variance is known or unknown, and by the way, it's almost always unknown. So my point there is that GARP will have to say to you something like, hey, here's the population, we know what the variance is. I think they explicitly will tell you that. But the point is here, for these two, here, let me go back here to this slide and this slide, is that once you put together a confidence interval, or once you put together the t or the z test, then you're going to arrive at the same decision because you're using the same inputs. Now, yet another way to do this stuff is to just look at the p-value. And the p-value, I always remembered p as in probability. That's why they picked the p. But it's a specific probability. It's the probability of observing a test statistic that is way over to the right or way over to the left. Small p-value like 0.005. That means the observed result is unlikely, and then you're going to reject the null. When I wrote my dissertation, I had collected all this data, threw it into the computer, and that spit out some regression analysis, and there was the p-value, and that was the first thing that I looked at. I was always looking for, give me 0.007 or some number. Of course, I was always looking for 0.007 because that was the James Bond number. So the important point here is that you can look at the p-value, and that pretty much summarizes all the other stuff that we have been doing in hypothesis testing and in confidence intervals. So here's just a quick example here. Suppose we are looking at market excess return. There's the null hypothesis, that equals 0. The test statistic, however we computed that, turns out to be 3.8. So here's our super simple formula to compute p-value. We're just going to take 2 because two-sided test, and we're going to multiply by 1 minus whatever that value is from the table. So we get 9, 9, 9, 4 9s and a 3. So there's the p of, 000 and 14. So that's super reject. So look at the third diamond point. We reject at the 5%. Now remember what I was saying back here. Always think of p-value as a probability, but think of it there in that definition. Don't think about it as the probability that the null hypothesis is true. That's an erroneous conclusion or application of the interpretation of p-value. That could be a good exam question. Now, how about if we want to test the hypothesis about two different population means? This is a better example, a more complete example of two people arguing, right? So look at what we have here. Compare fund returns versus the benchmark return. We have the benchmark over here, S&P 500 index, and we have our fund. And so these two people are arguing. One is saying, I'm better than you. The other one's saying, no, I'm better than you. This is a classic case of an argument which is maybe more applicable or at least more relevant or intuitive versus what I was saying earlier. Now look down at the bottom. When we do this test statistic, we have either related or unrelated samples. If they're unrelated, we call these independent samples, and they can be independent for two reasons. One reason is the obvious one, is that they have a zero correlation coefficient. The other reason is that one sample might have 27 observations and the other sample might have 95 sample observations. So then you have to kind of assign them an independent status. But many times we have these samples that are related. This chapter calls these paired bivariate, which means that they are probably correlated, but they don't necessarily have to be, but they probably are. And they're in the same period. Like if we want to compare, look at that third one there, stock returns versus bond returns during the same period. That would be a paired bivariate test. So here's the example of the stocks and the bonds. These are time periods, so there's the return level. And so, hey, are these two, are they identical or are they different? So let's suppose we have this bivariate variable. The important thing for you is to look at the test statistic down at the bottom. Notice we're taking the square root in the denominator because we have the variance. Now we've done that before. It's maybe looked a little bit different, but look at the third diamond point there. The idea is to test the mean difference. Mean difference. Let's call that z, and there's xy and yy. So when we take the difference between the two, the null hypothesis is going to be that it's zero. But these are two people who are arguing, and so one is probably going to be right, the other one is probably going to be wrong. So here's the test statistic that you're going to use. And in the numerator, this is the argument. X minus y equals 0. Or you could write it that x is greater than y or y is greater than x. Notice there are hats there to just reflect sample stuff. Now, in that bivariate model, what we're going to do in the denominator is remember that we've got to consider covariance. So we're going to do variance 1 plus variance 2 minus 2 times the covariance. And it's 2 times the covariance because x covaries with y and y covaries with x. Here's just a quick numerical example. We have excess returns, equity, and bonds. Month by month, n is 120. There's a correlation coefficient of 0.25. Equity has higher mean return and a higher standard deviation. That's logical there. So let's go ahead and say, you know what? The null hypothesis is that the mean excess return for equity is identical to the mean excess return on bonds. So what do we do in the numerator? The equity is saying, wait a minute, we're at 6.2. The debt is saying we're at 3.8. Well, if you take the difference between those two, clearly that's not 0. So you might be tempted to just say, well, there's no way that that they're equal to 0. Let's go ahead and reject the null hypothesis. However, don't be fooled by just the first moment of the distribution. We need to do the denominator. We need to standardize that difference. So instead of standardizing by just one standard deviation, we need to look at these two things as a portfolio. So we're going to divide and standardize by the variance of one plus the variance of other minus the covariance between those two. And notice we're going to divide by n there. So we get 0.59. So imagine that 0.59. That is less than 1.96, so we're going to fail to reject the null hypothesis. and we're going to say, you know what, these mean excess returns, even though 62 is different than 38, mathematically 62 is different than 38, but statistically, based on the standard deviations and their correlation coefficient, they are not. Interpretation, no evidence of significant difference. Now, if we have these mutually independent, if these are independent, well, we're going to use that same equation, but, and let me go back here, if they are independent, then the correlation coefficient and the covariance, that's 0. So, oh, and by the way, notice in the denominator there, we did 2 times the correlation coefficient times the standard deviation of one times the standard deviation of the other. Those 3 terms in parentheses, that's the covariance. But I'm guessing you guys remember that from a previous recording. So we don't have to subtract anything out because that covariance and correlation coefficient is 0. But now notice back here we had an N of 120 months. We had 120 months for equity. We had 120 months for the bonds. But now if they're independent, we might have 120 months for both of these things, but we might have, what did I say earlier? I can't remember those 2 numbers, 26 and 94. So we're dividing by the specific N for X and the specific N for Y. Now here's this last learning objective where I said I'm going to have a little bit of editorialization. So let me tell you about multiple testing. So suppose that you go and collect the data on our previous example with stock returns and bond returns, and you perform that test that we just did. Well, you have this data, so you might be tempted to perform a different test. And there are multiple tests that you can perform on the individual stock data and the individual bond data. And then there are different tests that you can perform on those too. Like, for example, you could test that the correlation coefficient, the null hypothesis might be the correlation coefficient is equal to 0. Well, the problem is that if you test this over and over using the same data set, sooner or later, you're going to make a mistake. And look down at the 3rd and the 4th. The mistake is going to be a type 1 error. So if you run lots of tests, you're going to increase the probability that you make a type 1 error. That, if there's a question on this learning objective, that just has to be the question. Whoops, sorry, I hit my button. What the chapter does is it has one of those gray boxes in there, and it gives an example, and it does all this stuff. And then in like 4 sentences, it gives solutions to the problem. So I'm going to give you kind of a editorial here. Maybe it has some comedy. So the learning objective, explain the problem of multi-testing, which I just did. How can it lead to the biased results? There's the type 1 error. But in the last 4 sentences of that gray box, there are some solutions to the problem. And so I read that box, and I promise you, I don't remember the Bonferroni or the home Bonferroni correction. I don't remember I don't remember any of this stuff. So I did a little bit of research on this just to help you, but I can't imagine that the Institute would ask you this question because it doesn't relate to the learning objective. It doesn't say, explain the problem, how can it lead to biased results, and then offer a solution. But if for some crazy reason this is part of a question, so remember this, that the Institute is very big on asking multiple questions in one question. So if it does do something like that, remember that this family-wise error rate, this is what I did in my research. I mean, the chapter doesn't tell you anything about these things. Family-wise error rate is, it has 2 components. You can either have false discovery or you can have the Bonferroni, and there are a couple of other tests out there. But what it does is they both try to control the probability of making any type 1 error. Now, what Bonferroni does and the Holm Bonferroni does is that it divides by the n, right? So multiple testing. So if you do 7 tests, instead of having an alpha of 0.05, the alpha is 0.05 divided by 7. That's the Bonferroni test. Have you tuned me out already? The false discovery rate, what this does is it orders maybe the p-value, and then it cuts it off. And what that does is it balances both the type 1 and type 2 errors. So I think if you just remember controls for false positives and type 1 and type 2 errors, I think you'll be fine. Anyway, if I would have gotten this question on the exam, I would have picked C and moved on with my life. Anyway, so there's the recap of our learning objectives. So I want you to go, as I always do, go to the end of the chapter, work on some of those problems. You'll have to do some calculations, but I think we covered all of that stuff. So remember, I don't want to go back to that, to one of those first slides, but remember the steps in hypothesis testing. I think the really good questions will come from that. So hey, thanks for watching, and as always, good luck studying.